Hello, today we're looking at the dynamics of rigid rotating bodies, and in a series of 3 videos we'll be covering the subjects of centre of mass, moment of inertia, angular momentum, torque, the parallel axis theorem and gyroscopes. Here is the x-axis. I'm going to keep this in one dimension for the time being to keep things simple. This is the origin, O, and I've got 2 masses. Mass m1, which is a distance x1 from the origin, and mass m2, which is a distance x2 from the origin. These 2 masses are somehow interconnected. In other words, the action of one has an impact on the action of another. It could be, for example, that they are gravitationally attracted to one another. Or it could be that if they are charged particles, there is an electromagnetic attraction or repelling between them. Or it could be that they are connected by a spring. Or it could simply be that they are connected by a solid rod. The point is they are somehow connected. And before we proceed, let's just remind ourselves that velocity is the rate of change of distance with time, dx by dt, and we represent that as x dot. X dot is just a way of expressing dx by dt. Acceleration is the rate of change of velocity with time, which is the same as the second differential, the second rate of change of distance with time, and that we express as x double dot. So x dot is really velocity, x double dot is acceleration. Now, if these masses are subject to forces, then they will accelerate. And we can say that with respect to the first mass, m1 x1 double dot is equal to the force on mass 1. And that is equal to the force on mass 1 by the object mass 2, in whatever way it is impacting, plus any external force acting on mass 1. Similarly, mass 2 times the second differential of x2 is equal to the force on mass 2, which equals the force on mass 2 due to mass 1, plus the external force acting on mass 2. Now let us add those 2 equations together, and that will give us that m1 x1 double dot plus m2 x2 double dot is equal to, I'm going to put it in this order, f12 plus f21, that's this one plus this one, plus f1e, that's this one, plus f2e, that's this one. And the reason I did that is because these 2 cancel out. They equal 0. The force on one by the other is equal to the opposite of the force by the other on the one. That's Newton's third law. To every action there's an equal and opposite reaction. The force by 1 on 2 is equal to minus the force by 2 on 1. And what is left is now just the sum of the external forces, which we can write as sigma external forces. So all the external forces added together are the force that creates this mass times acceleration term on the left-hand side. I am going to define a thing called x, capital X. It's a distance and it's going to sit somewhere on the x-axis. And my definition of x is going to be m1 x1 plus m2 x2 divided by m1 plus m2. Now m1 plus m2 is just the total mass in this system. So we can say that the total mass, which I'm going to call capital M, is m1 plus m2. What I propose to show you is that the capital mass, capital M for the total mass, times the second differential of this new term x, which is obviously the acceleration of x is going to be equal to the sum of the external forces. In other words, it's going to be that sum there. How can I show that? Relatively easily. What is m? It's m1 plus m2. So m1 plus m2 is m. What is x double dot? Well, here is x. m1 and m2 are of course constants, so they won't change with time. So we just have to do the differential, or the double differential of x1 and x2. So that's going to be multiplied by m1 x1 double dot plus m2 x2 double dot divided by m1 plus m2. It's the second differential of this term here. You can see that the m1 plus m2 terms cancel, and now we're left with m1 x1 double dot plus m2 x2 double dot, but that's what we had up here. And that, we said, is equal to the sum of the external forces. So this equals the sum of the external forces. So m capital X double dot is equal to the sum of the external forces. And now we can reveal what x is. X is the position of what is called the centre of mass. In other words, x is the position at which all the mass of a system or a body can be thought to reside. So if we look at this system up here, what we're saying is that you can think of m1 and m2 as a single mass, capital M, m1 plus m2, residing at a point somewhere along this x-axis. And essentially, instead of thinking of two masses separated, they behave as if they were a single mass operating at the centre of mass, which is point capital X. What happens if in this diagram m1 equals m2? Well, in those circumstances, if m1 equals m2 equals, let's call it just m, then x will be, here is our definition, but m1 is going to be the same as m2, and so x will become mx1 plus mx2 over the 2 times the mass. The masses all cancel, and you end up with x1 plus x2 divided by 2. And all that means is that the centre of mass is halfway between mass m1 and mass m2. That distance is the distance from the origin of the centre of mass. So far, we've just been considering two masses. But of course, there could be many. And the whole point about the definition of the centre of mass is that you can add as many terms as you like to this formula here. So in fact, x becomes more generally the sum of all the masses, let's say the ith mass, times the distance of the ith mass from the origin, divided by the sum of all the masses. That's the general definition of the position of the centre of mass. And you could have lots of masses in a system, and you can pick an origin anywhere you like. Let's say that's the origin, and if you take the mass of each individual particle multiplied by the distance of that particle from the origin, and you add up all those terms together and you divide by the total mass of the entire system, that will give you a value of x, which is the distance of the centre of mass, the point at which all the mass of the body can be thought to act from this origin. So what we're saying is that the distance capital X is the distance of the centre of mass from the origin. Right, so let me just write that down again. X is equal to the position of the centre of mass minus the origin. But suppose we put our origin at the point of the centre of mass. If we regard our origin is at the same point as the centre of mass, what happens then? Then x must be 0, because if the origin and the centre of mass are at the same place, x is 0. Now x is this term here. The total sum of the masses cannot be 0, so it's this term that must be 0. So when the centre of mass is placed at the origin, you've got the condition that sigma mi xi, the sum of the mass times the distance from the origin, which is also the point of the centre of mass, equals 0. And that is a conclusion that we will come back to later, so keep that in mind. How do you find the centre of mass of a two-dimensional object? With 3 dimensions it's slightly more difficult, but I can show you how to find the centre of mass of a two-dimensional object this way. What you do is you take the object and you stick a pin through it into the wall. So you pivot it somewhere, anywhere, it doesn't matter where you pick, somewhere here. Let's say we take that point there and we pivot the object on the wall. And the object will then swing. This is supposed to be the same shape, it probably isn't. It will swing backwards and forwards around this point. This is a pin sticking in the wall, pinning this to the wall so that it can swivel about that pivot point. And it will keep swinging until it comes to rest. When it comes to rest, you draw a vertical line down from the pivot point. And I assert that the centre of mass must lie on that line. You might ask why. Well, let's suppose it didn't. Suppose the centre of mass were there. The point about the centre of mass is that that is the point at which all the mass of this object can be thought to reside. So if all the mass resides at this point, then this becomes essentially a pendulum. And a pendulum with a bob here would not just come to rest there. It would swing backwards and forwards until eventually it came to rest underneath the pivot point, because that is when it is at its lowest potential energy. So the centre of mass must come to rest underneath the pivot point, just as a pendulum bob comes to rest under the point at which it is swinging, because that's where the potential energy is lowest. So we've drawn this line on the two-dimensional object. Now we take the pin out and we stick it somewhere else, like for example here. So now we've got the pre-existing line, say it's like that, and we put the pin in here. And once again the object will swing until it comes to rest. And when it does, we draw another line vertically below the pivot point. And I assert that the centre of mass for the same reason must be on this line. But since the centre of mass must also be on that line, which of course was that line, then the centre of mass must be here. So that's the way to find the centre of mass experimentally of a two-dimensional object. Now, no matter how oddly a body may behave, or a system of particles may behave, the centre of mass of that system will always obey Newton's laws. In the video that we did on projectile motion in our A-level physics revision series, we showed that if you throw a ball at an angle theta from the ground, it will travel something like that. This is the angle theta, and that's a parabola. Now let's take a tennis racket. A tennis racket has a shape a bit like this, and you can measure the centre of mass possibly using this method. Tennis racket isn't strictly two-dimensional, but it almost is, and you can find the centre of mass. And let's say that we paint the centre of mass red. So we paint a blob on the tennis racket where the centre of mass has been found to be. Now let's throw the tennis racket in the same way that we threw the ball. The tennis racket, of course, might spin over and over and over. It might do a kind of rotation movement as it's going through the air. Don't look at the tennis racket. Look at the red blob, which represents the centre of mass. And what you will find is that that red blob will perfectly describe the parabola. It will fully obey Newton's laws as the tennis racket is thrown. Now the tennis racket itself, of course, might be going round in all manner of circles. But the centre of mass of that tennis racket will remain on that parabolic line. Let's just remind ourselves that the distance of the centre of mass from the origin is given by sigma mi xi divided by sigma mi. And that, just to make it absolutely clear, is m1 times x1. In other words, the distance of m1 from the origin is x1, plus m2 x2 plus m3 x3 plus as many masses as you may have, divided by m1 plus m2 plus m3 for as many masses as you have. That's the definition of the position of the centre of mass. So now let's take a solid rod of mass m and length L. Mass m, length L. And we want to know, where is the centre of mass? Now you might take a guess and say, well, it's a uniform rod, so I guess the centre of mass will be in the centre. And of course you're going to be absolutely right. But let's see if we can calculate that using this principle here. And what we do is we split the rod into very many thin strips, each of which is a small distance delta x across. And let's just pick one of them to focus on. This is delta x in length, and it's at a distance x from the origin. We're going to make this end of the rod the origin. And of course the idea is that we make delta x get smaller and smaller, so delta x tends to 0. The mass per unit length of this rod, which is the mass divided by the length, is the one-dimensional equivalent of density. Density in 3 dimensions is mass divided by volume. Here we're only considering the x-axis, so we've got 1 dimension, and the kind of one-dimensional density is mass per unit length. So the mass of this little element here, which I'm going to call delta m, that mass is going to be the mass per unit length times the length of the little element, which is delta x. And we have said that the centre of mass is sigma mi xi divided by sigma mi. And how is that going to play out? Well, sigma mi is just the sum of all the masses, the sum of the masses of all these little elements. Well, that must be the mass of the object. So this just becomes capital M. When you've got a sum term for a continuum, you have to go to the integral. So this sum term is replaced by an integral from 0 to L, i.e. from 0 to the full length, of m over L times x, or xi, times delta x, which is replaced by dx. The m's cancel. The length is constant. L doesn't vary. L is a constant term, so that can now come outside the integral, and you've got 1 over L times the integral from 0 to L of x dx. And that is equal to 1 over L of x squared over 2, x dx. The integral of x dx is x squared over 2, evaluated from 0 to L. And that reduces to L over 2. So the position of the centre of mass is L over 2, in other words, halfway along this length is the centre of mass, which is what we guessed at the beginning, and we've been proved right. But this technique, as we shall see in a little while, is a useful way for finding out where the centre of mass is, and various other things too. Now you'll recall that we said that the centre of mass is the point at which all the mass of a connected set of masses, a system if you like, can be thought to act. And we showed that the external force on the system equal the total mass of the system, all masses added together, times the acceleration, which is d2 capital X by dt squared, or x double dot in this case. So no matter what the individual masses are doing, when you look at the centre of mass, you will find that that acts in such a way that the external forces will cause the centre of mass to accelerate according to this formula. Suppose that the external forces are zero. There are no external forces. There might be internal forces. For example, if there are two masses m1 and m2, they might be connected by a spring and they might be oscillating backwards and forwards according to the spring. But there will be no external force. That's just an internal force. Well, if the force is zero, that means that the acceleration is zero. That means there is no change in velocity, which means that mx dot, x dot of course is the velocity, is a constant. Because there's no change in velocity, because there's no acceleration, because there's no force. What is mx dot? Well, that's going to be the mass, which if we just think of our two masses as we had before, m1 plus m2, times x dot, which will be m1 x1 dot plus m2 x2 dot, divided by m1 plus m2. That's, if we take out that term there, this is just x dot. Once again, the m1 plus m2 cancels, and what you now have is that mx dot is a constant, and that constant is made up of the individual momenta of the masses. Mass times velocity is momentum. So that's just the momentum of mass 1. That's the momentum of mass 2. And that momentum is constant. It doesn't mean to say that these individual momenta aren't changing. Let's think of two masses, m1 and m2, connected by a spring. Now it may be that those masses are oscillating backwards and forwards. That may be, and the momentum may be constantly changing for each of those masses. But here's the point. If you look at the centre of mass, there will be no change in momenta. There will be either zero velocity or constant velocity, because there is no change. The momenta of the centre of mass, or momentum of the centre of mass, is a constant. Suppose that the external force is zero and that the velocity of the centre of mass is zero. What does that mean? Well, this is a situation which you get with the Sun and the Earth. Here's the Sun, here's the Earth going round the Sun. That's the Earth, this is the Sun. And the popular view is that the Earth goes round the Sun, whether it be in a circle or an ellipse that is very like a circle. That's the idea. But in fact, there is no external force. Forget about the effect of other planets. That's not important in this case. The only force is the force between, the gravitational force between the Sun and the Earth, which keeps the Earth in orbit. Now, there is going to be a centre of mass of this system, and that centre of mass will be between the Sun and the Earth. Because the Sun is so much larger than the Earth, the centre of mass is actually very close to the centre of the Sun. And if it were true that the Earth was simply circulating round a stationary Sun, if that were true, the Earth is going around a stationary Sun, then of course the centre of mass would have to go round the stationary Sun. But there is no external force acting on this system. Consequently, the centre of mass cannot move. So in practice what is happening is that when you've got the Earth orbiting and the Sun here, and let's say the centre of mass is here, what is actually happening is that the Earth is orbiting around the centre of mass, and so is the Sun. So the Sun goes round an orbit. It's a very, very small orbit because the centre of mass is so close to the centre of the Sun. But nonetheless, what is actually happening is that these two bodies, the Sun and the Earth, are, as it were, oscillating around a fixed point, which is the centre of mass. Let's now think about two-dimensional bodies. Two-dimensional bodies can have two types of movement. One is that they can move forwards, but they can also rotate. And you can actually get them doing both, as we saw with the tennis racket. You can throw a tennis racket in such a way that it forms a trajectory going forward, but it also tips over as it goes through space, spinning as it goes. Let's take a two-dimensional body. And we're going to pin it, as we have before, to the wall so that it can pivot around the pinned point. And what I'm going to do is to draw a line which is going to be along the x-axis, and that will have a distance, the length of that line is r. And now I'm going to swivel this whole object until it is pointing, the pivot point remains there. I've swiveled it about the pivot point so that the line is now here. And that will have gone through an angle which I'm going to call delta theta. And that point R will essentially have moved up through the arc of a circle, a distance delta S. That's still length R. So we've essentially rotated this whole body through an angle delta theta such that the outside point of the object has gone through the arc of a circle of length delta S, and it's done that in time delta t. Now, from our video on circular motion A-level physics, we showed that delta S divided by r equals delta theta in radians. That is the definition of an angle in radians. It is the arc length divided by the radius. So if we manipulate this, we can see that delta S is equal to r delta theta. Now, we covered the distance delta S in a time delta t. So let's divide both sides of this equation by delta t. Delta S divided by delta t equals r delta theta divided by delta t. Well, what's delta S by delta t? That's distance divided by time. Distance divided by time is velocity. And it's what one might call the rotational velocity. It's the velocity going round the circle as you rotate this body. So this is equal to v, the velocity, and I'm going to give it a little subscript, capital R, meaning rotational. What about this side of the equation? Well, that's r. Little r, remember, is the radius, times d theta by delta, delta theta by delta t. That is theta dot. And we give that a new term, we call that omega, where omega is the angular velocity. It's the rate at which the angle is swept out as we move the object round. And omega is measured in rads or radians per second. So velocity, of course, is meters per second. Omega, the angular velocity, is measured in radians per second. In the video on circular motion A-level physics, I also showed that centripetal acceleration, which remember is the acceleration towards the centre, it's not the rotational acceleration, it's the acceleration which is part of the force which keeps the body rotating. That is equal to the rotational velocity squared divided by the radius. But since we've just shown that the velocity is equal to r omega, we can substitute that v in here for r omega. We now get omega squared r squared over r, which of course is omega squared r. So the centripetal acceleration, which I repeat is the acceleration directed towards the centre, not the acceleration around the circumference, can either be expressed as the rotational velocity squared divided by the radius, or the angular velocity squared multiplied by the radius. Now let's take this formula, Vr is equal to r omega. I'll write that again, that's the rotational velocity is equal to the radius times the angular velocity. And now we will differentiate both sides with respect to t. The radius, of course, is fixed and unchanging, and so you get that dvr by dt is equal to r d omega by dt. The rate of change of velocity is just acceleration, but this is now the rotational acceleration. This is not the centripetal acceleration. This is the acceleration which tells you how much faster a body is going to go if you accelerate it. And that is equal to d omega by dt, which is the angular acceleration, alpha times r. So now we've got a link between the, as it were, the linear acceleration, the acceleration as you go round the circumference, as the object spins faster, and the angular acceleration, which tells you the rate of change of angle, or angular velocity. In the video Classical Mechanics A-Level Physics, we derived 6 equations, which I'm going to write down here, and I want to see if there is an equivalent in rotational behaviour. These are the equations. If you don't recognise them, I advise you to go back and look at the videos on Classical Mechanics A-Level Physics. But the 6 were as follows. V equals u plus at, where v is initial velocity, v is final velocity, u is initial velocity, a is acceleration, and t is time. S equals ut plus a half at squared. The only new term here is s, which is the distance covered. V squared equals u squared plus 2as. F equals ma, which we've actually used earlier in this video. Kinetic energy is a half mv squared. And momentum is mass times velocity. And again, we refer to that in this video. Now, if you take these two formulae here, the rotational velocity equals r omega, and the angular acceleration, the rotational acceleration is equal to the angular acceleration times r. And if you replace all the velocity terms by r omega and all the acceleration terms by alpha r, you'll find that the r's cancel out. And what you will end up with is that this term has an equivalent which says that the final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. This one becomes that the change in angle, theta, is equal to the initial angular velocity times time plus a half the angular acceleration times time squared. And this one becomes that the final angular velocity squared is equal to the initial angular velocity squared plus 2 times the angular acceleration times theta, the change in angle. We will now go on to show what the equivalent in rotating systems exists for these 3 terms. First, I want to think about kinetic energy in rotating systems. I've got a system which consists of masses, 3 masses, m1, m2 and m3, and they are going to be connected by massless steel rods. So they are fixed, and I'm going to pivot them at this point here. So this whole system can swivel about this point here. And I'm actually going to rotate it with an angular velocity of omega. And there is no angular acceleration. So in other words, it's a constant angular velocity. Now, what is the kinetic energy of that total system? Well, the kinetic energy will be the sum of the kinetic energy of the three masses, which means you can write that as a half sigma MIVI squared. So it's a half mv squared for each of those three masses, where I goes from 1 to 3. But we have shown that V is equal to omega r. So we can substitute that in there, and that gives us a half times sigma mi omega I squared r squared. And now here's the important point. I can remove the I from the omega because all these masses will rotate with the same angular velocity. They won't rotate with the same rotational velocity because that depends on how far away they are from the origin. But they all go round with the same angular velocity omega. And that therefore gives us that the kinetic energy is, I'm simply going to rewrite this term here in a different way, sigma mi r squared times omega squared. And this term here, the sigma mi r squared, I'm going to give a new name. I'm going to call that I. So now we've got that the kinetic energy is a half times I times omega squared. And if you look, that has a similarity to the normal form of kinetic energy that we speak about, half mv squared. And the reason is that this term I has a kind of a mass equivalence, just as omega, which is the angular velocity, is the, as it were, rotational equivalent of linear velocity. And that I is called the moment of inertia. So the moment of inertia is equal to the sum of mi ri squared. There should incidentally be an I up there, as there should be an I here, because it's the radius of the ith point. Just to be clear, you multiply each mass by its distance from the pivot, and those are different distances, which is why you have to have an ri squared for each mass. Now, here is a critical point. That moment of inertia is critically dependent on where you put the pivot. You could put the pivot here. If you were to do so, the moment of inertia would change. The moment of inertia depends on where you are actually regarding the centre of the swivel point, the pivoting point. Mass, of course, doesn't change, but the moment of inertia will change depending on where you have the pivot. We also wanted to find a rotational equivalent for momentum. Momentum is mass times velocity. And I should have said P is equal to mass times velocity. Is there then an equivalent in rotational terms? Well, yes, mass has an equivalent. We said it's the moment of inertia. And velocity has an equivalent. It's the angular velocity omega. And that is what's called the angular momentum. And that's given the letter L. And just like ordinary momentum, angular momentum is also conserved. Then finally we wanted to know if there was a rotational equivalent to F equals ma. Well, again, the mass has the equivalence of the moment of inertia. Acceleration has the equivalence of angular acceleration. And when you multiply the moment of inertia by the angular acceleration, you get something that is the rotational equivalent of force, and that is called a torque. Now, if a torque, which is represented by the letter tau, is equal to I alpha, Alpha, of course, is the rate of change of angular velocity. So tau is actually equal to I times the rate of change of angular velocity, which is d omega by dt. But I d omega by dt is simply the rate of change of angular momentum. I d omega by dt, if you differentiate this term by dt, then you differentiate this term by dt, you get dl by dt is I d omega by dt. And so what we've shown is that the torque, tau, is equal to the rate of change of angular momentum, just as force in linear classical mechanics is the rate of change of ordinary momentum. So there are rotational equivalences for all of Newtonian laws. Suppose two masses, m1 and m2, are connected by a metal rod and are pivoted at this point here. In other words, we put a pin through the rod and the whole thing can swivel around this point here. And suppose I apply a force perpendicular to the rod at this point here. There's my force. What will happen is this rod with the masses at the end will swivel about that point. And so it will end up something like this. And let's say that I swivel the rod through an angle d theta, and that means that the point at which the point at which I apply the force goes around an arc length of delta s. And we'll say that the force is applied at a distance x from the pivot. What is the work done by me in causing this system to rotate through an angle delta theta? Well, the work, of course, is the force times the distance. That is the definition of work done. So if you like, delta W, which is the work I'm doing, is force times distance, which is delta S. But as we've shown before, that is the same as the force times x delta theta, because remember, delta S over x is, by definition, delta theta in radians. What is the kinetic energy that that system has now gained? Well, we just derived that. The kinetic energy is a half I omega squared. It's the equivalent of a half mv squared for linear motion. And I just showed you that there is a formula that omega final squared is equal to omega initial squared plus 2 alpha delta theta. In the case of this movement here, the initial frequency or angular velocity was 0. We started it from scratch, as it were, stationary. And so now we've got that omega final squared equals 2 alpha times delta theta. And I'm going to take that omega squared and substitute it in here. So now I've got that the kinetic energy is a half times I times 2 alpha delta theta, which is what I got from here. But now I can say that the work done is equal to the kinetic energy achieved, because work is just converted into energy. So this term, fx delta theta, this term is going to be equal to that term. Work done is kinetic energy achieved. You can see that the 2's cancel out. You can see that the delta thetas cancel out, and that leaves us with fx equals I alpha. But we just showed that I alpha was the torque. So the torque is now the force times the distance from the pivot point. the force times the distance from the pivot point is the torque. And we'll need to remember two terms here. Firstly, we need to remember this one because we shall use this later. And we'll also need to remember that the torque is the force applied times the distance from the pivot point. Suppose I take exactly the same system as I have here. So we've got a rod with two masses at the end, mass M1 and M2, pivoted at this point here so that they can swivel about this point. But instead of applying a force perpendicular to this rod, I now apply a force at an angle theta. And the force is applied at a distance x from the pivot point. That's a distance x. Now we showed before that tau is equal to the force times the distance. But that was when the force was perpendicular. When you get to this point, you've actually got to consider what is the component of this force. Well, the force will resolve into two components. This one, which is the one that's perpendicular, is F sine theta. There'll be another force, F cosine theta, acting along the rod. In fact, it will be pushing the rod away from the pivot point. And that is completely wasted, because as long as the pivot point is strong enough, pushing away from the pivot point along the rod achieves nothing. The only force that has any relevance here is the force that is perpendicular to the steel rod, and that's the one that's going to cause it to swivel. And so whenever you apply a force not perpendicular to the rod, then this equation here becomes that tau is equal to not just the force, but the force times sine theta, times the distance from the pivot point x. So that's the more general form for the torque. It's the force times the sine of the angle between the force and the rod, as it were, times the distance from the force and the pivot point. And if you've got several such forces, then the total torque on the system will be the sum of all the forces, all the distances from the pivot point, and the sine of the angles associated with each force. And that gives you the total torque on the system. And before we move on, notice one important point. If you have a force acting through the pivot point, it has no effect. The reason is that the torque for a force acting on the pivot point will be the value of the force multiplied by the sine of the angle, that's all right, multiplied by the distance between the application of the force and the pivot point. But if the force is acting at the pivot point, x will be 0. So any force which applies through the pivot point will have a torque of 0. Now I just want to remind you what we showed you a few moments ago. We said that the work done was equal to the force times the distance between the application of the force and the pivot point, provided the force is perpendicular, times delta theta. And we also said that provided the force is perpendicular to the rod that we're pushing, Fx is the torque. So that equals the torque times delta theta. And we'll need this for what we're doing next. I want us to consider what is essentially a pendulum, a rigid rod which is massless, and at the end we have a mass m. And it's pivoted at this point here. And what I'm going to do is to push this mass up so that it rotates to an angle theta 0. And the question I want to ask is, what is the work that I do pushing that mass up through that angle theta 0. Well, let's consider any interim point in that journey where we've gone through an angle theta. This bob has a mass m, and that will therefore be exerting a force vertically downwards, the gravitational force mg. And you can resolve that in two directions. This one will be mg cosine theta, and there will be one moving in that direction, the, as it were, restoring force, and that's mg times sine theta. Now once again, mg cos theta is having no effect whatsoever because it's essentially pulling on the rod connected to the pivot point. So it has no effect, it can't extend that rod as long as the rod is strong enough. The only force that's actually having any effect is the restoring force that is what I'm actually pushing against to push the pendulum up. And that is mg sine theta. So tau, the torque, is equal to the force, which is mg sine theta, times the distance, which of course is the length of this rod, which I'm going to call L. So essentially the torque is the force multiplied by the distance from the pivot point, which is the length of the rod, which is L. And then I said that delta W, the work done, is equal to tau delta theta. So now we've got that the work done will be, and here we've got to integrate from this position to this position. So now we're going to have to do an integral of tau d theta, which is mg sine theta times L d theta, and we go from 0 to theta naught. Well, m and g and L are all constants, so they can come outside the integral. M, G, L are all constants. And that leaves us now an integral between naught and theta naught of what's left, which is sine theta d theta. The integral of sine theta is minus cosine theta, and so we get that the total work done is mgl multiplied by minus cos theta evaluated between naught and theta naught. And when you put that into the equation, you get that the work done is mg capital L into 1 minus the cosine of theta naught. But what is the increase in potential energy of this mass now that it has gone up this distance? The distance it's moved up is a distance h. And so you would say that the potential energy is going to be mgh. So let's just write that down. The potential energy that mass now has, or the increase in potential energy to be precise, is mgh. And that's going to be mg into, well, what is h? H is the length of the rod minus this bit of the rod. And that bit of the rod is L times the cosine of the angle theta naught. Right. This distance here is equal to L, which is this distance here, times the cosine of that angle, which is theta naught. So H is L minus L cosine theta naught. So H is L minus L cosine theta naught. And that's equal to mgl into 1 minus cosine theta naught, which you'll notice is the same as the work done. And that's perfectly reasonable. I do that amount of work, consequently the actual system itself, or the mass at the end of the rod, gains the same amount of energy. Let's go back to our massless rod with two masses at each end, M1 and M2. Once again, we pivot it at that point, and this time we're going to apply two forces, but in opposite directions. This is F1, this is F2. F2 is at a distance x2 from the origin, or from the pivot point. F1 is at a distance x1 from the pivot point. The total torque is going to be the sum of all the Fi, Xi terms. But since these forces are pushing in opposite directions, that means the torque is going to be F1 x1 minus, as F1 x1 minus F2 x2, because the forces are in opposite directions. We remind ourselves that tau is equal to I alpha. We showed that earlier, which means that alpha, the angular acceleration, is equal to tau divided by I, and that is going to be F1 x1 minus F2 x2 divided by the moment of inertia. So that's the way you can determine the angular acceleration of a system like this. If, of course, you know the moment of inertia, and that's what we're coming on to. So let's take some basic two-dimensional shapes and ask ourselves, what is the moment of inertia of that shape? And of course, that will depend on where you do the pivoting. I remind you that we determined that the moment of inertia is sigma mi Ri squared. That's the mass times the distance from the origin for all the masses associated. Let's first consider a thin ring. That is to say, I'm drawing it much thicker than I should, just so you can see. This is empty space in the middle. The ring is simply this bit here. And we're going to assume that somehow we can rotate it around this point here. Maybe it has just one or two very lightweight spokes, such that we can rotate the thing through the pivot point in the centre. The mass of the ring is mass m, and the radius of the ring is r. And we say that I is equal to sigma mi Ri squared, where mi is the mass of a little element carved out. In fact, we break the ring into lots of elements, all the same size, all the way around the ring, and we consider the mass of each of those times the distance of each of those from the centre. Well, this is actually fairly trivial, because the radius is always r. All of these little elements are all exactly r from the centre. So Ri squared can be replaced by the radius squared. And what is the sum of all the masses? Well, the sum of all these individual masses all the way around the ring is the mass of the ring. And so you find fairly simply that the moment of inertia of a ring which rotates around a pivot point at the centre of the ring, then the moment of inertia is mr squared. Let's now do something a little more complicated than that. This time we're going to do a disk, a two-dimensional disk. And again we're going to rotate it around the centre of the disk. And we want to know what is the moment of inertia of that disk. To find out, we construct a very thin ring which is a distance x from the centre. Incidentally, the ring has mass m, and the total radius of the ring is r. If we take this very thin ring, it's going to have a circumference of 2 pi times the radius, which is x. So the circumference is 2 pi x. So if we, as it were, unravelled that very thin ring, we would get something of length 2 pi x. And we're going to say it's very thin, it's going to have a thickness delta x. So I'm going to call this thickness dx. What is the area of this very thin ring? The area is equal to the length times the depth, 2 pi x times dx. What is the mass of this thin ring? Well, the mass, which I'm going to call delta m, is equal to essentially the area density, which is the total mass divided by the total area. The total area of a ring, of course, of a disk is pi r squared. So that's the, as it were, the two-dimensional equivalent of density, mass per unit area rather than mass per unit volume. And you multiply that by the actual area of the ring, 2 pi x dx. So that's the mass of the ring. It's the mass per unit area times the area of this ring. And then you say that the moment of inertia is equal to the sum of mi ri squared. And this is the mass of all the rings. We're going to have rings going from the middle right the way out to the outside. So you're going to have the sum of mi, which will be m over pi r squared times 2 pi x dx, times ri squared. Well, ri is simply the distance from the ring to the centre, which in my terms here we've called x. So x squared is essentially ri squared. And because this is continuous, once again, the sigma becomes an integral, and so you get that the moment of inertia is equal to, well, we can take the pi's cancel. We can take the 2m over r squared outside because those are all constants. They're not going to need to be integrated. And now we go an integral from 0 to r, from the centre of the circle out to the outside, of x squared times x is x cubed dx. And that will be 2m over r squared, which is this term here. When you integrate x cubed, you get x to the 4th over 4, evaluated from 0 to r. And when you do that, you will find that that equals mr squared over 2. So now we've found that the moment of inertia for a disk which is rotating around its centre is mr squared over 2, whereas the moment of inertia of a ring, thin ring, also rotating around its centre is mr squared. What about a regular rod of mass m and length L? And we're going to rotate it around one end. Once again, what is its moment of inertia? Moment of inertia is sigma mi squared, or sorry, mi xi squared. I'm going to split this rod up into lots of elements, just as we have done before. And we'll consider just one of them, which is going to be a thickness dx and a distance x from the pivot point. The mass of that little element here is going to be the mass per unit length, which is the one-dimensional equivalent of density, times the length itself, dx. And that means that the moment of inertia is going to be the sigma m, which is m over L dx, times x squared. But of course, because it's continuous, that now has to become an integral. So the moment of inertia is equal to, we can take the m over L outside because those are constant. And now we replace the sigma, the sum, by an integral from 0 to L, because we're going from here right the way to the end, L, of x squared dx. And that is equal to m over L of x cubed over 3, because if you integrate x squared you get x cubed over 3, evaluated from 0 to L. And that will be m over L times L cubed over 3, or since the one of the L's will cancel, that will be mL squared over 3. And that is the moment of inertia of a rod which is swivelling about one end. Remember, it matters where the pivot point is. So this only applies if the rod is swivelling and the pivot point is at one end. Incidentally, it's worth just noticing before we press on that since the moment of inertia is always equal to the sum of a mass times a distance squared, that every moment of inertia should have dimensions mass times distance squared. And so far, that's right. This has got mass times distance squared. The ring has got a mass times distance squared. It may have an divided by 2, but the dimensions are right. And here we've got a mass times a distance squared divided by 3. But if you ever get a moment of inertia where the dimensions are not mass times distance squared, you've made a mistake. Now I'm going to take this rod, but this time I'm going to pivot it in the centre. So here is the same rod of mass m and length L, but this time it's pivoted in the centre so that it swivels about the centre. And once again I'm going to split it up into lots of different elements, all of thickness dx, and they are going to be of a distance x from the pivot point. And I want to know what is the moment of inertia now. Moment of inertia, just to remind you, is sigma mi xi all squared. Well, the mass of the little element, as before, is going to be the mass per unit length times the thickness, which is m over L times dx, so that's the mass element, and the distance is always going to be xi squared. So the moment of inertia is going to be sigma of all these values. And that, once again, because it's continuous, we replace it by an integral. So now you've got an integral not from 0 to L, because it goes from minus L over 2 to 0, since this is the, as it were, the origin. So minus L over 2 to 0 and 0 to L over 2. So the total integral now is from minus L over 2 to plus L over 2 of this term here, m over L x squared dx. Well, where you're going from minus L over 2 to L over 2, you might as well just go twice from halfway. So that's the integral from 0 to L over 2 times m over L x squared dx. All I did was to say this is from minus L over 2 to plus L over 2. So if we go from 0 to L over 2 and multiply by 2, we'll get the same result. Once again, I can take the m over L outside because those are constant. So now we get 2m over L times the integral from 0 to L over 2 of x squared dx. And that's equal to 2m over L. The integral of x squared is x cubed over 3. And that is evaluated between 0 and L over 2. And if you calculate that and work it out, you will get that the moment of inertia is mL squared divided by 12. So our dimensions are right because it's still a mass times a distance squared. But that is the moment of inertia when you pivot the rod in the centre and swing it around that central point. And you can compare that with a rod that was pivoted at the end, where the moment of inertia was mL squared over 3. So as I said, the moment of inertia critically depends on where you pivot the rod. And that potentially makes it very awkward, because what it means is that every time you've got an object and you want to put the pivot point somewhere else, does that mean you've got to do a long, complicated calculation to find out what the moment of inertia of that self-same rod, but simply pivoted at a different point, is going to be? And the answer is no. There is a simple way of determining the moment of inertia about any point, that is, the moment of inertia about any point that you choose to use as the pivot point, as long as you know the moment of inertia around the centre of mass. That's called the parallel axis theorem, and that's what I'm going to start with in part 2 of this series of 3 videos.